Hello everyone and welcome back to our discussion on the fundamentals of particle and fluid solid processing. And we started our discussion on the fundamentals of colloid and nanoparticles. We started our discussion with the Brownian motion, the surface force. At that we started with the van der Waals forces. We have seen the genesis of van der Waals force, that is the dipole moment, how it is created, and how it achieves its lowest free energies configuration, and that resulted in this van der Waals forces, the attractive forces between all the dipoles of the two particles resulted in the combined overall attraction, and this we say is the van der Waals interaction force. Now, this, as I mentioned, can be attractive or repulsive in nature depending on the dielectric properties of the particle and the intervening medium. So, the pairwise summation of all the interactions basically it provides us a simple expression that is analogous to the overall interaction between two spherical objects or spherical particles of same size and that are separated by a distance which is very small compared to their size. So, in this criteria, the van der Waals interaction energy can be expressed or has been estimated by this expression. So, this is the van der Waals interaction energy and this is the van der Waals force expression, where A is the Hamaker constant. Now, this schematic shows that the particles say are of two different material, that is particle 1 and 3 are separated by an intervening media, that is 2. Now, this positive value or the negative value of this force, that means attractive or repulsive nature, and its magnitude would depend on the value of this Hamaker constant here. Now, this if Hamaker constant is greater than 0, the interaction is attractive. If Hamaker constant is less than 0, then this interaction is repulsive in nature. So, which means this Hamaker constant is calculated for this system, say two materials separated by an intervening medium. Now, this in this case the material 1 can be of this 3 is equals to 1, this can happen. That means, there can be two materials, material 1 and material 1 separated by material 2. But this is more generic configuration, say two different particles separated by an intervening medium. Hamaker constant is calculated based on such scenario. Now, a typical values of these Hamaker constants are given in this table. So, what is noteworthy in this table? So, in this table actually we have different material, say the alumina and alumina are separated by air. In this case, we have a certain Hamaker constant value, which is in the order of 15 multiplied by 10 to the power minus 20 joule. In case of silica, this value is lower, which is 6.5 into 10 to the power minus 20. The interesting point is that when we change the intervening media, say for alumina when we change from air to water, this Hamaker constant value goes down. It is the positive, the attraction is there, but it is of lower attraction or lower force, attractive force in practice. Now, this has the implication in our application. The scenario is that, so these fine powders of alumina, when they are in contact with air, they are cohesive in nature, and that is done by this van der Waals interaction of having higher Hamaker constant, which means higher interactions, and that is these are more cohesive in nature, difficult to flow. As we change the intervening medium to water, we say the attractive forces has decreased, which means these particles are now easier to separate. The attractive forces has been reduced. It can now be easy to separate them. Similarly, for silica particles, we can see the similar difference. From 6.5 to 0.7, it has been reduced when we change the medium from air to water. So, these metals, when they are in water, this has a significantly higher Hamaker constant value, which means they are attractive in nature. So, this air, these are the air bubbles, say in water. This also, now we have spoken about this solid particles. Now, in this case, this air and water, this air bubbles or say the oil droplets also can be considered as particles to estimate the interaction in between them by this theory. And that is why the Hamaker constants are listed here as well, to give you an idea of their strength between say the air bubbles in water, or say the oil in water emulsion and water in oil emulsion. Now, the point here, the rare case that I have mentioned, that the van der Waals can be repulsive in nature if we have the Hamaker constant as negative value, which is shown here. So, here the scenario is something like that, that the silica particle, okay, attached say to a air bubble and being separated from water. In that case, the separation becomes difficult. So, then we have the negative Hamaker constant, and as we mentioned here, that means there is repulsive interaction. So, this provides us an idea or the reason behind that why separation of say alumina or silica particles in water becomes easier than when that is in air, or why the fine particles in contact with air is more cohesive than it is in water. Now, the other force that is very critical or dominant is the electrical double layer force. We say it is the EDL force in short. Now, the particles can develop a surface charge when it is immersed in a liquid. Say the case of a metal oxide particle, when this is exposed in air or in contact with air, okay, the atoms at its surface will have some insufficient or say unsatisfied bonds, and they will try to arrange themselves like here in this one, where M stands for the metal ion, this is positive, and oxide is negative. So, something like this, MO, 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 this kind of configuration when it is in simple air or pure air or in vacuum. Now, when there is moisture in air or some humidity in air beyond a certain percentage, this will react with the water, or say it is immersed in water, then in that case this will react with water and will create the metal hydroxyl groups, and then these metal hydroxyl groups, depending on the pH of the solution, which means higher pH means alkaline solution, lower pH means acidic solution, depending on these two medium, it will further react with those H plus ion or the OH minus ion, and in case of low pH the configuration would look like this kind of a scenario, where it would create MOH2 plus, something like this on the surface, and in case of high pH, that is alkaline medium, it would create MO minus or higher density of this kind of surface charges. Now the point is that this surface ionization reaction constant, which are A and Ka and Kb in this case, are the material properties. It depends on the properties of the material. For example, it changes with silica oxide, it changes with alumina oxide. They have the different values. So the point is, there is an isoelectric point which is called IEP, where we have the mostly neutral sites on the surface, that is zero net charge on the surface, which is this kind of a scenario. Here we have mentioned that as a water, considering pH as 7. But this is again material specific. There will be a different value of IEP for each and every material, under which there will be the net surface charges and the neutral sites will dominate, but there will be occurrence of this positively charged ion and the negatively charged ion, but the total balance of between these two will be nullified. The numbers will be same. But at low pH, the surface hydroxyl groups, as I mentioned, will react with H plus and form the positively charged surface. This is the low pH case, which means the acidic medium. And at high pH, these hydroxyl groups will react with OH minus and will form negatively charged surface, which is MO minus. So the density of these charges on the surface is negatively charged, and here we have positively charged surfaces. Now this schematic shows the variation of pH and the number of sites per unit area. And this point, where the maximum numbers of OH simple hydroxyl group exist, is the IEP or the isoelectric point. At the low pH than this, dominance of positively charged surface. Higher than that IEP, we have negatively charged surface. And these are the different materials and their approximate IEP values. So we can see the silica has the IEP of 2 to 3. Alumina, on the other hand, we have 8.5 to 9.5, that is on the higher side. Oil and air is in the order of 3 to 4. So that means depending on this material, we have different IEP values, and if the media is higher than that or lower than that, depending on that we have a surface charge development on the surface of these particles. Now, when we try to separate the charge between the surface and the bulk solution, there is a potential difference that is called the surface potential. Now, these counter ions that actually forms a diffuse cloud around each particles maintains the neutrality of the system, and each solution, or say each particle or each surface charge will have its counter ion. That means, say here we have the positively charged surfaces. So, which means the counter ions in this positive cases, it can be the KOH solution which will provide us the OH minus. When that there is, say, negatively charged O minuses are there, the counter ions can be the HCl solution which will provide us the H plus ion. So, these counter ions actually keeps this solution or the particles electrically neutral state. Now, when we try to say bring them closer, there will be the overlapping of this counter ion clouds, and that actually increases the concentration of the counter ions in the gap between the particles. If the particles are of same charge, then there will be a repulsive potential due to this osmotic pressure of the counter ions. This repulsion is known as the electrical double layer repulsion. So, surface charge has been developed, but these are kept neutral by the addition of counter ions. This counter ions creates a cloud around each and every particle. Now, when we try to keep these or put these particles together or in close proximity of them, then this overlapping of these diffuse clouds or the counter ion clouds increases the concentration in between the particles, concentration of the counter ions, and if the particles are of same charge, then it actually repulses them. This counter ion thickness and its repulsion we call the electric double layer repulsion. It is quantified by the Debye length. So, it is a measure of this electrical double layer thickness, basically this Debye length, and it also provides a measure or estimate on the range of this repulsion force or the repulsive force, where this kappa is the Debye screening parameter, and for monovalent salts this is written in this form, or this has a relation with the molar concentration of the monovalent electrolyte. So, Debye length provides the measure of this electrical double layer thickness, which also tells us the range of this repulsive force. So, large Debye length, that means the small counter ion concentration, which means the particles are repulsive in large separation. And if we add some salt to it, it compresses the electrical double layer because there will be an increase in concentration of the counter ions. Once the sufficient amount of salt is added, this electrical double layer repulsion then decreases and the van der Waals interaction becomes dominant. So the concept here is that when this Debye length is large, which means we have small concentration of the counter ions around the particles are repulsive, say, at a larger distance. Once we add the salt, say we have added some salt, then this double layer thickness is compressed because now we have increased the concentration of the counter ions. Now if we add sufficient amount of salt, this ideal repulsion decreases and the van der Waals attraction again dominates. So this ideal for surface to surface separation distance of d in between two spherical particles of same diameter and surface charge can be written in this form or has an expression of this one, where epsilon is the relative permittivity of water and epsilon 0 is the permittivity of the free space. Which is related here, the energy for the potential energy for electrical double layer is related with the surface potential. So which means we have to measure the surface potential as well in order to have its magnitude. Now this expression is valid for constant surface potential, which is below about 20 millivolt, and the other criteria is that the separation distance is much smaller than the particle size. If it is not, then it creates some complex expression. So which means to estimate this ideal potential energy, we have to know now the surface potential that results from the surface charges. So this surface potential, direct measurement of it is not trivial. It is difficult because there is a layer of immobile ion and say the water molecule layer is present. Instead, we measure zeta potential, which is the potential at the plane of shear between this immobilized ion surface layer and the bulk solution. And the distance between this actual surface and this ion layer surface is of about few angstrom. So it provides us a near about accurate measure of the surface potential as well. This zeta potential can be measured by measuring the velocity of the particles under a electrical field. So this schematic shows the variation of zeta potential with salt concentration and pH. We see as the salt concentration increases, zeta potential decreases. As the pH increases, the zeta potential also decreases. And this is how a solution or suspension is manipulated for its surface charges to create, say, aggregates, to create flocculates. So the other force that is important is to control the surface force between the particles in suspension by addition of soluble polymer to the solution. Now, say we consider the polymer's affinity towards the particle surface and it absorbs on the particle surfaces depending on the molecule weight and the amount that is being absorbed. So, depending on these parameters, that is the polymer molecular weight and the amount it is being absorbed on the particle surface, there we can have attraction or repulsion. Attraction due to polymer bridging or repulsion due to steric interactions. So, when we try to control the surface force, we can also add some soluble polymers to the solution. If we consider, say, the polymer has affinity towards the particle's surface and it absorbs on the particle surface, and then depending on the amount it is being absorbed and its molecular weight, that means polymer's molecular weight, we can have attractive force or the repulsive force between the particles. These are the separate forces than this van der Waals force and the ideal forces. And this absorbing polymer layer that creates the interactions can be repulsive or attractive in nature. Based on this, say the attraction, we have bridging flocculation or the steric repulsion. So, we will continue discussing on these two aspects, that is the bridging flocculation or the attraction and the repulsion or the repulsion. Okay, why this happens, how it happens, we will continue our discussion in the next class. Till then, thank you for your attention.